Welcome to This Explainer. Today, we're diving straight into the absolutely crucial first phase of building software. We're going to put on our hats and take on the role of a tech detective to really decode requirements and structure analysis. So, if you've ever wondered how a completely messy, real-world problem gets transformed into a clean, functioning app, you are definitely in the right place. Okay, let's kick things off by asking a foundational question. How can you possibly create a complex system if the person paying for it only has a super vague idea of what they actually want? Seriously, it happens way more often than you think. The client knows they need something to fix their problem, sure, but they don't speak the language of code or system architecture. To answer that, we're going to walk through 6 key phases today. 1. The tech detective. 2. Gathering the clues. 3. The software rulebook. 4. Mapping the data flow. 5. Digging into details. And 6. The final blueprint. All right, let's jump into section 1, the tech detective. This whole journey begins with the system analyst. Before writing a single line of code, literally not one line, this detective has to make sure client expectations are perfectly documented. They do this using a strict 4-step requirement engineering process. It all starts with a feasibility study, basically asking, is this project even practically and financially possible? If the answer is yes, they move on to gathering the actual requirements, writing out the software specifications, and finally validating those requirements to make absolutely sure no one is asking for the impossible. Moving right along to section 2, gathering the clues. If that feasibility study gives the project a green light, analysts start figuring out what the software must actually do. And they use a rapid-fire toolkit to do it. We're talking everything from open-ended interviews and task analysis to good old-fashioned brainstorming sessions. They might even use prototyping, which is basically building a bare-bones user interface without the background code. That's a lifesaver for clients who just can't visualize their own needs until they physically see it on a screen. Or, they might just sit and observe the client at their workplace to see firsthand how they deal with workflow bottlenecks. But there's a pretty big hidden danger when it comes to survey questionnaires. While they are fantastic for mass data collection, like, say, surveying an entire department's needs all at once, there is a major catch. If an option for a specific issue isn't listed as a checkbox, a critical requirement might just be left completely out in the cold. Essentially, you only get answers to the questions you actually remember to ask.
That brings us to section 3, the software rulebook.
Once all those clues are gathered up, the detective has to strictly categorize them so the developers know exactly what to build. The absolute crucial point here is understanding the difference between functional requirements and non-functional requirements. Functional requirements define exactly what a system does. Think of a search bar, or the ability to print a sales report. Non-functional requirements, on the flip side, dictate how well it does it. This covers all those implicit expectations, things like speed, security, and storage capacity. To put this into perspective, a functional requirement is what lets a user click a button to register for a class. But a non-functional requirement? That's what ensures the system can actually handle 2,000 of those registrations every single second without crashing, or that it can automatically restart within 5 seconds of a virus detection. Both are totally essential, but they focus on entirely different layers of the software experience. All right, on to section 4, mapping the data flow. With the rulebook written and all those requirements validated, we transition from gathering clues to drawing a map of the territory. We do this using a data flow diagram, or DFD. Now, what's fascinating about a DFD is that it completely ignores how a program is controlled step by step. It doesn't care. Instead, it focuses purely on how data moves. It tracks incoming data, outgoing data, and stored data as it zips between different entities and processes in the system. Depending on the specific standard you use, like DeMarco and Jordan or Gain and Sarsen, analysts map this data out using very specific symbols. You're going to see circles or rounded rectangles for discrete processes. Those are the actions actually transforming the data. You'll see squares representing external entities, like customers or an external inventory system. And you'll see open rectangles for data stores, which are essentially just the files or databases where the information rests. But beware, there are strict rules to this map making. You can never, ever have a miracle where a process magically outputs data from thin air. You also can't have a black hole where data goes in and just vanishes into the void forever. And crucially, data absolutely cannot move directly between 2 external entities or 2 data stores without a process in the middle. Something has to actually do the work to move that data. Let's move to Section 5, digging into details. To see how this builds, we usually start from a bird's-eye view. This is called a level 0 or context diagram. It represents the absolute highest level of abstraction. The entire course registration system is just a single process bubble right in the middle, simply numbered 0. It's just interacting with external entities, students sending in course selections, and teachers receiving registration details. It is the ultimate big-picture view of the whole system. But if we crack open that level 0 bubble and zoom into a level 1 DFD, we start to see the internal logic. The student's registration form flows into an availability check process. That process then interacts with a course's data store to see if there's actually space. Then it flows into an enrollment process, updates a student data store, and finally outputs a confirmation letter back to the student. We are finally seeing the gears turning inside the machine. Which brings us to our final section, the final blueprint. So we've gathered the clues, categorized the rules, and drawn the map. Now it's time for the final handoff. Because visual diagrams can sometimes still be misinterpreted by different people, analysts often use what's called structured English to write out the complex logic. This uses plain English words but wraps them within a structured programming paradigm, like if-then-else statements. It's a really clever way to describe exactly what needs to be coded without writing the actual code itself, bridging that understanding gap and helping programmers write error-free code without any confusion. As we wrap up this explainer, I want to leave you with a bit of a challenge. Take a look at the software you use every single day. Your banking app, your favorite food delivery service, your social media. Imagine yourself as the tech detective. What are the hidden, non-functional requirements keeping that app running smoothly? And if you had to draw a level 0 context diagram, how is the data really flowing behind the screen? Keep asking these questions and you will absolutely never look at software the same way again. Thanks so much for joining me.